the main conclusion. Well, uni or bidirectional exchange flows develop in transitional environments and occur when two other bodies with different densities are connected by a submerged channel. An example of this kind of flow can occur in sea straits and river estuaries. And you have several cases in which this kind of flow develop all over Europe, cases of sea straits and estuaries. When the width of the channel is large, you can have that the Coriolis effect due to rotation of Earth can affect the flow dynamics and can induce secondary flows. In addition, when the bottom of the channel is made by an irreducible bottom, the interaction of the flow with this irreducible bottom causes a change in the shape of the bottom, and also the change in the shape of the bottom can affect the flow itself, affecting also the mixing processes occurring at the interface between the two layers. Then, with this project, we try to address two main scientific questions. The first one is how do these bidirectional exchange flow dynamics can be affected by a change in external forcing parameters. A change in these external forcing parameters can be due to climate change, and these external forcing parameters are freshwater flows, density differences, and Coriolis effects. The second scientific question is what are the reciprocal feedback mechanisms occurring between the two-layer exchange flow and the mobile bed? We performed the experiments. We performed experiments at the Coriolis rotating platform in Legy. This is a unique experimental facility, letting us to perform these experiments with taking into account the Earth rotation and the ambient fluid rotation. And it's possible to run experiments with stratification that mimic transitional environments. And the tank is a cylindrical tank with a diameter of 13 meters, a depth of 1.2 meters, and inside the tank it was positioned the channel that we used to run the experiments. The channel has a trapezoidal cross-section, and at the two inlets, at the two sides of the channel, two different flows with two different densities were fed. Then a salty flow on the bottom and a freshwater flow on the top, in order to have this two-layer exchange flow. In addition, the bottom of the channel, there was in the bottom of the channel a sediment trap that led us to perform experiments with and without sediments. The movie is available on the Hydrolab Plus web page. You can have a look. It's described the project that I'm describing now. Well, measurement techniques. We used, I think, all the measurements instruments that were available at Legy. We collected everything, and we used particle image velocimetry and laser-induced fluorescence to measure instantaneous velocity and density fields in different sections spanning the width of the channel. We applied dye visualization technique. It's a simple technique, but we needed to use it because it's a very complex phenomenon. Nobody was investigating this kind of flow before. Then, in some cases, we had to understand what was happening in the tank before planning our measurements. We also used acoustic Doppler velocimetry and microconductivity probes. We coupled these two measurement techniques in order to get profiles at the same location of both vertical profiles of both velocity and density. And we use laser bed scanning to measure the bed morphology. That's a sketch of the tank we used. It's a top view. You can see the red grid is the area where we applied laser bed scanning in the middle of central area of the channel. In the same area, the green area, we applied particle image velocimetry, and these lines are the different sections where we measured by PAV vertical planes of velocity. And The black line is a transversing system over there that is enlarged here, where the different probes, both conductivity and ADVs, were positioned in order to get these vertical profiles of both velocity and density. This transversing system was moved along the channel in order to get these measurements in different locations. The experiments. We performed 4 series of experiments. The first series is a base case dealing with bidirectional exchange flows in a no-rotating and rigid bottom channel. That is the base case. After that, we performed the second series, then bidirectional exchange flow in rotating rigid bottom channel. And in this case, we took into account rotational effects only. In the third series of experiments, we positioned a mobile bed. Then these are experiments with bidirectional exchange flow, no rotation, and sediment bed. And the last set of experiments couples both rotation effects and sediment bed, then bidirectional exchange flows in rotating channel with an erodible bed. And the experimental parameters that are external forcings that were varied are the fresh water flow. We tested 3 values, including 0. That means that with 0 value of QF, we have a unidirectional exchange flow or a gravity current. We didn't vary the salty water flow. We varied the density of the salty layer. Then we tested 2G prime reduced gravity value. And we varied the rotation rate. Okay. First results. Here I show you on the top PIV velocity measurements in the middle of the channel. Here you have a sketch of the cross section, and this is the position of the PIV measurements that I show you in the slide. Is it in the middle of the channel? Here we have no rotation, and we are changing the fresh water flow. And what we found is that by increasing the fresh water flow, the effect on the bidirectional exchange flow is to decrease the thickness of the salty layer. We evaluated also the interface between the 2 layers, and you can see again the effect is that the thickness of the salty layer flow is decreased due to the presence of a fresh water flow that increases, and the interface is defined in this case by analyzing PIV velocity measurements by the 0 velocity value. And here I show you the effect of rotation on 2-layer exchange flow. On the first plot, we maintain constant the fresh water flow, where this dimensionless area, 4.5, and we varied rotation. The effect on this 2-layer exchange flow over rotating flow of rotation is to have a slope in the interface. Then we have as the rotation rate increases, the slope of the interface between the 2 layers increases. And if we fix rotation rate, and we have a look to what's happened to this 2-layer exchange flow and to the interface between the 2 layers, by increasing the fresh water flow, we found that this inclination of the interface due to rotation is enhanced by an increase of the fresh water flow. These are velocity measurements for the case of a unidirectional exchange flow. That means a gravity current. On the left, we have the case of no rotation, then different sections. You can see here the section, where are the sections? These symbols means that the flow is coming outside from the screen, okay? And when you have rotation, you have that the current is deflected to the right. But well, with no rotation, we have that the top section here, we have 3, that is located on the sloping side wall of the trapezoidal cross-section, has no salty layer flow. You can see there is no flow in this top section. The flow is in these 2 sections, as I put this. If you add rotation, what's happened? The flow, as I told you before, due to Coriolis effect, is deflected to the right, And you have flow also here in the section on the trapezoidal side. And the thickness of the salty layer increases while the velocity decreases. I'll show you here for the same run than a gravity current, no flow on the top, fresh water flow on the top, a comparison of vertical profiles of velocity for different rotations, and in a section that is located here, close to the right of the channel. And at the same location, we have also vertical profiles of density. What happens if the rotation rate increases? We have that the maximum velocity decreases and the thickness of the salty layer increases. That confirms what we found in the previous plot. And for the density, what we found is that as the rotation rate increases, the thickness of the mixing layer developing between the two fluids at different densities increases. For the experiments with a mobile bed, we performed also measurements of the bed morphology, both at the beginning and at the end of the run, by applying a laser bed scanning technique. That means that we use the same laser that we used to measure instantaneous velocity fields to scan the bed. We recorded the scan and by analyzing these images, we were able to get bed elevation. And here is an example of a result of application of this technique. Then we have a picture of the bed and the bed elevation evaluated by laser bed scanning. And you can see that there are bed forms developing on the bottom that are due to the interaction. This is still a run with a gravity current and no flow, fresh water flow on the top, only a salty layer moving on the bottom of the channel with rotation. Okay. Then in this case, what's happened? These bed forms developing on the bottom of the channel are not symmetrical with respect to the channel center line. The bed forms deviate on the right, and this is due to the flow that is affected by the Coriolis effect, deviates to the right itself and interact with the bottom and causes this kind of bed form pattern. If you increase the rotation rate, then the effect of Coriolis, you can have a kind of flow meandering pattern developing within the salty layer. This is a very complex pattern within the flow. We didn't expect it, and this is the reason why we had to use the visualization. We really didn't expect to get this. It's an unstable, completely unstable condition due to the interaction between the salty layer and the bed. Then the bed is deformed and interacts with the salty layer that mixes and interacts. Then there are feedback mechanisms. And in this case, this is the bed elevation that we measured at the end of the run. You can see the starting region here, the region over there, and this is a complex bed pattern that is associated to a complex flow that is developing in this case. And here you can see the picture related to the same case, meandering. Then, conclusion. I showed you some preliminary results that you got from our transnational access. We performed several experiments, and then I focused on these two kinds of flows, then the effect of Coriolis and freshwater flow on both bidirectional exchange flow and increase of gravity currents. What we found is that an increase of the freshwater flow for bidirectional exchange flow causes a reduction of the thickness of the salty layer. Coriolis effect causes an inclination of the interface between the salty and fresh water flow. And in addition, this inclination is enhanced by an increase of the freshwater flow For gravity currents, that means that we have an ambient fluid, a top ambient layer that is not moving. What is moving is only the bottom salty flow. We have, again, an inclination of the interface, and we have that the current moves on the right, and we have a decrease of the maximum velocity, an increase of the thickness on the right, and an increase of the mixing layer thickness. And for large rotation rates, in case of gravity currents, we found the developing of this meandering pattern that affects deeply the change in the bed in case of sediments. And this is the research team. We spent 2 months in Grenoble running experiments. It was I'm very happy to have spent this time there. It was a very, very nice time to spend. And I told you we are from Italy, UK, Estonia, France, that was hosting us. More than 50% of the team were women. And that's it. Thank you.
So, questions? Yes.
Maybe I missed it, but what's the grain size of the sediment?
It was very, very fine because the velocity were very low. Then we used as sediments PIV particles that were polyamide particles, 300 microns.
Low density.
Density, it was 1020.
I was wondering the pattern that you see developing.
Yeah.
They also develop it in a more realistic sense.
But,
You showed morphology in the end.
yeah.
So it's very complex pattern.
Yeah.
But do you expect such a similar pattern when you have more realistic?
It depends. No, well, the pattern is caused by the flow. Then
probably inversion, right?
Yeah. Then this kind of flow, that is the meandering pattern, developed also without sediments. Okay, but it was more steady. With sediments, it was more complex because there was an interaction with the mobile. And it's a kind of instability in the flow that develops when the rotation effect is large. We had a Rossby number of 0.1 for this case. Okay, then if you want to know if it's happened, it could happen in real cases, but you need to check depending on density, width of the current, what's the Rossby number. Because the rotation is not varying. It varies, the rotational effects are varying with latitude. Then at large latitudes, you can have more effect of the fluid. Okay?
But you are talking about dune formation?
No, but maybe from misunderstanding. I thought the morphology is more to show apparently the flow pattern, right?
Yeah.
No, but the threshold for dune formation is directed by the shield number. And I think this can be compared to nature because the density is smaller, but the velocity is smaller. So
yeah. No, we were on the threshold of if you want to know, we were on a little above the threshold of movement of those sediments. Okay, if you want to compare to shields, they are in the case of almost critical conditions.
For the no sediment cases, did you see any evidence of shear instability in the interface? I noticed that you had density profiles and velocity profiles. In principle, you can get a number of profiles.
Yeah, this is what we want to do. We still did not analyze these couple of groups, both velocity and density, but the aim is to do exactly this. But we need to analyze the data. Yeah.
Okay, so thank you.
Thank you.